Very good talk. You use the laws of physics to predict what's going to happen billions of years from now. Can you use that same methodology to calculate what happened 4.5 billion years ago?
Yeah, so the interesting thing about Newton's laws is that they're perfectly time reversible. So in the same way that we have visibility into where the planets were or will be, say 150 million years into the future, we can also recompute their orbits backward about 150 million years into the past. And indeed, if we do that, for instance, and look at the tilt of Mars, we can correlate the patterns on the Martian surface of alternating ice and sand with climactic variations that it underwent as a result of its orbit. And we can see what was going on. But in the same way that we can only make probabilistic trajectories going forward after 150 million years, we can only make probabilistic assumptions of what happened in the very early days. So we can't kind of run the solar system back to its initial condition. We lose sight of what happens about 150 million years in the past.
The neat thing about that is we have some evidence previously, but we won't have any evidence ahead of us. So we could maybe check out the theories by looking at things like
and so,
the ice of Mars and things like that.
Yeah, so there's a lot of interest in doing that, and Mars provides a great, we have great eyes on Mars, and so this calibration of the orbital dynamics, we have good confidence that it's right because of how well it does in explaining the Martian obliquity variations.
I would have thought that going backwards you have greater accuracy because you know where it is. But anyways, my question is, are we in line for a second moon?
Well, there's about a 1% chance that the Mercury will go unstable within the next 6 billion years. And if that happens, there's about a 1% chance that the outcome will be Mars crashing into the Earth. And so that would lead to, that would be a moon-forming event. So the answer is,
similar to what formed the original moon.
Yeah, so the chances of that are about 1 in 10,000. And I started the talk with kind of going on about French guys and mathematics. And one of my favorite things was Buffon, the Comte de Buffon, and I think it was 1840. He said that 1 part in 10,000 is the lowest interesting probability. And that's true. Right? It's just like if something is less than 1 part in 10,000 of happening, I'm not worried about it. I'm not worried about asteroids crashing into the Earth. I'm not worried about that kind of stuff. There's like a less than 1 in 10,000 chance. Okay.
Okay. So I'm curious about the weather prediction. It's increased from 6 to 8 days. So how much of that is coming from better observations versus better models and more computing power? And going forward, like how much better is it going to get 10 years from now? And how much is improvements going to come from more computing power, or is it just a bottleneck the measurements at this point?
So I was studying up on this pretty intensively last night, trying to prepare for this talk. And from what, I mean, I don't do weather prediction for that's the part that I'm least familiar with in this talk. But what it seemed to me is that it's really equal parts better initial conditions, so there's more radiosondes and there's more kind of weather stations. Because of the ease of getting data from far-flung locations, we can have more weather stations kind of feeding into the models. So there's the better initial conditions, and you mentioned all 3 effects. There's faster computers, so you can, with a faster computer, you can do a higher resolution model and get it done in time, right? If it takes you 2 weeks to predict the weather tomorrow, right, you're out of luck. So computer speed is really an issue. And then there's better algorithms. So there's better physical modeling of what's going on, which you can do if you have faster computers. So you can have things be less approximate. And so my understanding is that all of those effects are improving the quality of the models. And usually these things kind of have a logarithmic behavior in the sense that you get most of your improvement with the less amount of work, and that you get, for 90% more work, you get 10% more improvement and so forth. So my guess is that barring some kind of quantum computing or something that would give you an extra few days, that we would see kind of a 2-week prediction be the asymptotic limit. And that's really, you're starting to bump up against the fundamental aspect of the butterfly effect. So yeah, we're not going to get twice as far into the future with exact weather prediction.
Has anybody looked at the various planetary systems, the moons of Jupiter, the moons of Saturn, and if so, which is the first one where we don't know far, or which is the closest one to reaching a point where we don't know?
So interestingly, our own solar system, as you pointed out, kind of has a whole set of solar systems. You have the regular satellite systems of the Jovian planets. Those are all extremely stable. And interestingly, the outer planets, Jupiter, Saturn, Uranus, and Neptune, form their own, effectively, solar system. They don't talk very much to the inner solar system. Or, I'm sorry, the inner solar system doesn't talk very much to them. They push the inner solar system around. The inner solar system doesn't have much of an effect on them. Jupiter, Saturn, Uranus, and Neptune stable for an incredibly long period of time. If we didn't have the sun evolving, they would last for about 10 to the 18th power years. Whereas the inner solar system is unstable on something like a 10 billion year, 100 billion year time scale. It's 1 million times less stable than the outer solar system. So the answer is it's the inner solar system, Mercury, Venus, Earth, and Mars, that's the most unstable configuration within our planetary system.
Thank you.
You've used the phrase the sensitivity to initial conditions as a basis for a lot of the predictions, but
yes.
How do you define the initial conditions? Because, I mean, for instance, with the weather predictions, I tend to look at the Weather Channel app about 50 times a day, hoping for rain. And even when it predicts rain, a half hour later, it might say, well, now it's down to 10%, and now it's down to 4%.
So, yeah, and I've noticed that on the iPhone, too. And that I don't know, the iPhone predictions.
Well, this is a Weather Channel, the predictions are coming from
there seems to be a certain stochastic element to those. Okay. But it is true. It is true that if you look at the national weather model, that it's doing a good job up to a couple days into the future. And then it also makes kind of probabilistic statement. So when you say there's a 10% chance of rain, it means that 9 out of 10 times it won't rain.
Right.
So you can't predict whether a particular cloud in front that you're coming is going to precipitate all the way to the ground. So I think that part of what we're seeing there is those sort of micro climate effects. So it's a thorny problem in the sense that it depends on exactly what your initial conditions are. If your initial conditions or your requirement for prediction is that how much rain am I going to get at this particular spot, then your ability to predict is less than is it going to rain in the Bay Area 3 days from now. And I think that when we talk about weather prediction, we're talking about the more general statement, is it likely to rain in the Bay Area 3 days from now, rather than is it going to rain in Menlo Park, at this particular time.
But are the initial conditions, I mean, a specific point in time?
Yeah, it's the way things are at a particular time, right? So the initial conditions for the weather are all of the atmospheric patterns right now. So all the weather fronts, all the wind speeds, the sun's shining on one side of the earth, not shining on the other side, the ocean currents, all that stuff defines our initial conditions. And then laws of physics take those initial conditions and run them forward through time.
So for other things, as not considering the weather, but some of the other things you've been talking about, initial conditions change all the time, so predictions change all the time.
The Pythagorean Three-Body Problem is I use that because it's much easier to sort of talk about what you mean. The initial conditions there are the locations in space where the three bodies are located. And so the initial condition for the problem is the 3, 4, 5 right triangle. And the sensitive dependence on initial conditions means that if you turn it into a 3, 4, 5.0000001 triangle, that the solution won't always stay the same. It will gradually get more and more and more different until eventually it's completely different.
Hi, yeah, with regard to general relativity providing that extra stability, is there anything significant or deep about that?
Yeah, we're here.
Well,
no, right? If there was a 70% chance that the solar system goes unstable, then there'd be a 7 out of 10 chance that we wouldn't be here to observe the solar system. So there's nothing deep in the philosophical sense, zero. But it's interesting in that we're living in a solar system that's stable, but not slam dunk stable, and that kind of what we really need not to be worried is provided by the general relativistic corrections. So it's cool, but not deep.
Just to expand on the question that was raised before, what about the other object in the sky there, the lunar Earth system? How stable is that? I mean, you think that's clearly had a very chaotic origin. It's got a very complicated interaction with a body which is not spherical, which is actually changing its shape with reaction. So what's the future?
So the Earth-Moon system, that's another very interesting whole other lecture. And so the evolution of the Earth-Moon system is dictated in large part by the tidal dissipation in the Earth. So we have tides twice a day. The tides are dissipating the Earth's spin energy. And so the moon is being pushed outward. Its orbit gets larger by about 3.5 centimeters per year. It's gradually spiraling outward.
Wow.
But because of the dissipative action of the system, it's more predictable than it would be otherwise. A good way of saying this is you may have seen a double pendulum. And a double pendulum comes out like this, and then there's another pendulum to attach to it. And it kind of does these wild swings. If there's no dissipation in the system, it's a great example of a chaotic sensitive dependence on initial conditions. You can kind of predict what will happen for a couple swings into the future, but then it becomes harder and harder, and eventually you lose all predictability. But if there's friction, I can tell you exactly where that pendulum is going to be 2 hours from now. It's going to just be hanging down like that. Right? But it's true. It's totally true. Right? Dissipation is what's required to remove this sensitive dependence on initial conditions. And instead of having a divergence, you have an attraction. Right? And so the Earth-Moon system is easier to predict its action because it's subject to dissipation.
Just from watching the weather, I've gotten the impression that the predictability is much better if it's one single weather system. And that if it's multiple weather systems, the predictability, both in the accuracy and the distance into the future, starts to degrade pretty seriously.
Yeah, that's probably true. I don't know that much about the weather. So it sounds reasonable to me.
So I'm not sure if this is really within the range of your talk, but you mentioned that Laplace had said that the universe was in essence totally deterministic, which left no room for free will, but then Poincaré showed that we couldn't predict.
Yeah.
Is the thinking then, and this is sort of philosophical, but does that leave the door open then for free will?
Yeah, well, I think, so something that this was a wide-ranging talk, but one thing I didn't touch on at all is quantum mechanics. And so the universe has a kind of a probabilistic structure and uncertainty and indeterminism built into its very microstructure. And so I think that any discussion, a discussion I'm not qualified to have, but any qualified discussion about free will, I think necessarily has to bring quantum mechanics into the fold. This talk that I've given is like 19th century stuff. Like it's 19th century stuff dressed up for the 21st century with fast computers. And you can get a long way with that, but I didn't mention quantum mechanics once. And so, that's a whole nother café scientifique.
Thank you.
Well, this follows up on that question exactly. What can you do with quantum physics in terms of predictability, and where does the whole concept of randomness fit into that? See,
I've answered 11 or 12 questions, and one of them I kind of stumbled around. The weather one over there, I don't know. I don't know.
Shall I go next? You mentioned that there was a fifth planet that met up with the Earth, and that created the moon.
Yes.
But that was billions of years ago?
Yeah, that was, so the Earth is 4.54 billion years old. And that collision probably occurred 10, 20 million years after the Earth itself kind of accreted pretty much to its present mass. So that was something that occurred very early in the history of the solar system.
But then you also said you could only predict backwards about 150 million years. So
yeah.
How do you know that?
Oh, because, so that has nothing, our knowledge of the moon forming event has nothing to do with orbital integrations or anything that I talked about here. There's a number of lines of evidence. The moon seems to be made of very, very similar material to the Earth's mantle, which is what you expect if you have collision between two differentiated bodies where the iron core of the impactor kind of slid like an egg yolk in and joined the Earth's core, and the mantle material formed a disk which eventually formed into the moon. There's a lot of isotopic commonalities between the rocks that were brought back by the Apollo astronauts and compared with Earth astronauts. There's a whole, I'm not an expert on this, but there's a whole basically corpus of geophysical evidence that the origin of the moon was in a giant impact. I would say it's not for sure, but I think that we have something like 99% confidence that that's what happened. No, there was a separate planet, and the mantle of that planet and the mantle of the Earth were mixed, and then now that our moon has made a material that is very similar to the Earth's mantle material, and they're both a mixture of the two original bodies. That's nice.
So a lot of your talk kind of centered around the idea of when does predictability kind of halt.
Yeah.
But you never really spoke about how do you define that? Like, when do you say, how do you measure that and say, this is the point where I no longer know? Because even before then, it's kind of
that's right.
thing.
So there's a somewhat elastic definition. But in terms of the stock market, let's say, can I predict with, say, 95% probability that the price of the SPY ETF will be higher than now 10 milliseconds from now? I can do that if I have access to all the infrastructure that's needed to get the data fast enough on the microsecond timescale. I can make that prediction. I can't tell you with any certainty whether the price of SPY will be higher or lower than it is 2 minutes in the future. Right? So it's the predictability sort of scales with the problem that you're looking at, but it's basically with some confidence can you specify the state of the system in an interesting and useful way, some number of information crossing times from now. That would be the way I would define it.
And just a follow-up, do you think that that's strictly decreasing in time, or do you think it can, so in other words, do you think there could be multiple points where you could predict something?
So in general, it strictly decreases in time, but there are interesting systems, and this is related to something called the KM theorem, where you have kind of a oscillation around the perfect solution. So in some sense, you do get predictability for long periods of time. But those are very special systems that they have a mathematical interest, but not really a physical interest. I think for physical systems, they're generally messy enough so that predictability always fades away unless there's dissipation in the system, which is driving it towards some sort of dissipated end state, fixed point.
So in the case of the stock market, get some useless information out of this. So just on theoretical basis, I mean, given initial conditions, as you said, your ability to predict degrades quite rapidly. But in the particular case that you looked at, it seems like there is this group of very active traders, high frequency trading, who are using this millisecond or microsecond information to then act on the stock market.
Yep.
So, and how does that feedback affect the predictability?
So on a given day, you look at like, they create there's like 17 or 18 high frequency traders who have the infrastructure to do this. On a given day, the interactions of their strategies kind of create an equilibrium, which, if you can beat them, allows you to get stuff, predict what's going to happen a few milliseconds into the future. That whether it's a few milliseconds or 5 milliseconds, 10 milliseconds, depends on what's happening that day, and it depends on how they've adjusted their strategies. The strategies are constantly evolving. And so this touches on another talk of static dynamic equilibria that's going on there as well. So yeah, the answer is that it varies from a few milliseconds to a few tens of milliseconds. For instance, Hurricane Sandy, which I showed, went through and knocked out the microwave networks. And if you look at the data, it turns out it knocked them out for 5 days. And so for those 5 days, the predictability was quite a bit better because that information was traveling more slowly. It was going on fiber optic cable. So it was 3 milliseconds slower. And also, because the situation was different, it seemed like a lot of traders pulled out. And so the market was a simpler structure for those couple of days, and it was more predictable. If everything was going right and you had all your infrastructure wasn't knocked out by Hurricane Sandy, then you could have cleaned up on those several days. So it changes from day to day. But in general, it's not of order minutes, it's not of order years, it's not of order nanoseconds, it's of order milliseconds.
Let's give Dr. Laughlin a hand. Thank you so much.